Today I'm going to be talking about work that I've been doing largely with Matula Hanaf, and I should point out that this talk will be sort of a part one. Matula is giving a seminar tomorrow, which will sort of complete the work that we're going to present. So today I'll be presenting results that demonstrate the importance of correcting errors and biases in ocean initial conditions for improving intensity prediction. And also, we'll be looking at the importance of assimilating ocean observations for improving these initial conditions and intensity forecast. First, I'd like to acknowledge the support that this work has received from the Quantitative Ocean Observing System Assessment Program, the Sandy Supplemental 2014, Hurricane Supplemental 2018, the AOML Glider Program has provided support to this modeling work, and also acknowledge divisional support at a PHOD. Yeah. Okay. Skip one. Okay. Now, for motivation, I'm going to go back and present some results from an earlier study where we looked at the impact of ocean model initialization errors on Hurricane Ivan. And this study showed very clearly that ocean model initialization errors are the most important factor that degrade model SST forecast under hurricane forcing. This work was published in Monthly Weather Review in 2011, but it provides a good background to our present work. In this particular ocean response study, we forced the ocean with the HRD H-wind product for all the experiments, and this was representative of Hurricane Ivan forcing. We ran a control experiment that was initialized by a realistic ocean analysis, Navy Global HICOM, using ENCODA assimilation. We then prepared a group of alternate experiments, each varying a single model attribute. We looked at different mixed layer models. For example, KPP model was in the control experiment. We looked at two other models. We varied horizontal resolution, vertical resolution in the mixed layer, the surface wind stress drag coefficient, surface enthalpy flux coefficients, and different initializations with control using the ENCODA realistic analysis, and the second initialization was an unconstrained model. First, the results from the control experiment were actually fairly good. On top, you see the sea surface height present during Hurricane Ivan. We have a medium extension of the loop current, a detached ring that existed to the west of Ivan's track, and very clearly two energetic cold core cyclones were present at that time. Now, the middle panels show pre and post Ivan SST from the TMI AMSRE product from remote sensing systems. And before Ivan, you have very uniform SST over the entire Gulf. After Ivan, you see the cooling pattern with the two regions of very strong cooling associated with the locations of the two cold core rings. Now, the model, the ocean response experiment that we ran, we again see nearly uniform SST pre-storm. But after the storm, the ocean model produced fairly realistic pattern of SST cooling given the initial ocean conditions. So, and again, initializing the ocean correctly is very necessary to do that. Now, to illustrate this, I'll show some results from some of the other alternate experiments. First of all, these panels show the difference in SST cooling between the alternate experiment and the control experiment. So from the top panel, when we reduce the vertical resolution in the mixed layer, you see this was the difference in SST cooling that occurred by making that one change to the model. The second panel is where we changed the vertical mixing scheme from KPP to GIS, and you see again the change in SST cooling, differences of several tenths of a degree Celsius along the storm's track. The third panel, we changed the drag coefficient to calculate the wind stress forcing, and again you see differences of up to a degree Celsius along the track. Now, when we change the initialization from a realistic to an unconstrained model, you can see by far that had the largest impact on the SST cooling that was forced by the idealized Hurricane Ivan forcing. And just for completeness, this shows all of the cases, and on the bottom you see the results from unconstrained initialization. The bias, and I should point out that these are averaged over that box shown there. By far, the bias in the cooling and the RMS difference in the cooling much larger for the initialization. So the point I want to make here is that, again, initialization is the most critical factor to get right in the ocean model. And also, the difference is so large that without accurate initialization, it's going to be very hard to try to use ocean observations to try to improve ocean model performance. If the initialization is bad, the ocean model response is bad, and you can't really correct or take action to correct the ocean model performance if the initialization is bad. So it's critical to get the initialization correct. Now, this leads into, of course, subsequent work. The limits, of course, of an ocean response study is that we don't know what the actual impact of those ocean model differences are on predicted intensity in coupled models. So we need to develop the capability of performing controlled coupled forecast studies where we can vary the initial ocean states, but initialize the model with a constant initial atmospheric state. And this enables by leaving the atmospheric state unchanged, this isolates the ocean contribution. And we can begin to look at what matters in terms of ocean model initialization and intensity prediction. A key step in this development was performed when Jilly Dong was here, and in collaboration with EMC, he developed the capability to initialize the HICOM H-WRF model at EMC with ocean fields that we could provide from our ocean model analyses. Okay, so the outline of the rest of this talk. In the first part, I'm going to summarize the results of several earlier studies that emphasized the sensitivity of intensity forecasts to model initialization. I'll very briefly mention the work Jilly Dong did with Hurricane Gonzalo, but he also ran an analysis for Hurricane Edward in 2014 that's received less attention. I'll present those results here. Work I did with Hyun Suk Sim at EMC involving Hurricane Blanca in the Eastern Pacific. I'll show some results there that clearly illustrate sensitivity to initialization. And then I'll briefly summarize some work that was done with Shyama Mohanty from the Indian Institute of Technology when she was here for visiting AOML, where we looked at sensitivity of idealized Bay of Bengal storms to different ocean initial fields. And after that, I'll begin to look at our more recent work, and I'll present results from ocean observing system experiments for 2017 and 2018 Atlantic storms. In today's talk, I'll emphasize the ocean results, but tomorrow, Matu Lahanaf is going to discuss the coupled forecast runs he's performing to look at the actual sensitivity of ocean forecasts to different initial states. And we'll be getting down to the nitty-gritty of trying to look at individual ocean observing systems and how individual observing systems can affect the intensity prediction. But stay tuned tomorrow. Okay, summarizing work that Jilly Dong performed here. Gonzalo results, of course, I think we're all very familiar with those, where we looked at two different initializations, realistic and unconstrained, with the same atmospheric model initialization. But the Edward work, I think, is quite interesting, where he focused on the sensitivity of predicted intensity to interannual variability in the state of the ocean. And to do that, we looked at different ocean model initializations, one with ocean climatology, and then 5 realistic ocean states representing the years 2010 to 2014 on the initialization day and time of Hurricane Edward. So, and the atmospheric model initialization was, again, the EMC operational initialization. So only the ocean state is varied. And very quickly, we're familiar with this, but this work clearly demonstrated the impact of ocean model initialization, whereas without data assimilation, the upper ocean was too cold, so the heat potential with observed on the left was clearly too low, and with the data assimilation, we obviously much more realistic, and as we've seen, that leads to a significant improvement in the intensity forecast. But I'm going to look now at this interannual study that briefly that Julie encountered. And here we see 6 different model initializations. Upper left is the Navy ENCODA product, the realistic initialization for 2014, and these are maps of SST. And we had, and from left to right, 2013, 2012, lower left, 2011, 2010, and then climatology. So generally, each year was, I don't think any year was cooler than normal, but 3 of the years, 2014, 12, and 10 were fairly significantly warmer than normal. So the question is now, how much does this difference in initial ocean state make to forecasts where we hold the atmosphere constant? And these are the results for minimum pressure on the left and maximum wind speed on the right. The black curve is the best track, the observed intensity evolution of Eduard. The blue curve is the climatology, and that's obviously climatology, since the ocean was much warmer than normal, the climatological initialization led to a weak storm. But the interannual variability matters. The 2 warmest years of 2014 and 2012, you see much more realistic intensities. Whereas the coolest of the years, which would be 2011 and 2013, the response is closer to climatology. So the answer is yes, and the differences here are 22 millibars and 30 knots typically when the storm reaches its maximum intensity. So we see quite a significant influence of the existing ocean state in a given year, given the fact, holding the atmosphere constant to.
Those are H-WRF forecasts?
Yes, these are all with HICOM H-WRF. I think that's pretty much true for almost most of these analyses, right? And the second earlier study with Hyun-Suk Kim looking at the sensitivity of Hurricane Blanca in the Eastern Pacific to ocean initialization. And she ran 2 cases where two initialization procedures were compared. The realistic analysis was from the NOAA Real-Time Ocean Forecast System product. And it was compared to what they call the feature-based analysis, which is the old method they used to initialize the hurricane model. Now in the Atlantic, they artificially insert loop current and eddies in the Gulf of Mexico, which is why they call it feature-based. But outside of that region where they put the features in, the initialization is basically climatology, but with SST relaxation. But the SST relaxation only corrects temperature in the mixed layer, and in the case of Blanca, did not accurately initialize the anomalously thick surface warm layer that was present associated with El Nino conditions in that year. And again, the atmospheric model initialization in these cases was the same, the operational EMC initialization. The heat potential, pre-Blanca, the RTOF's initialization in the upper left, and the TCHP analysis. This is TCHP in both cases. The analysis in the upper right, and you can see the RTOF's initialization was fairly realistic, whereas if you compare the conditions to climatology in the lower right, you can see how much warmer than normal the upper 100 to 200 meters of the ocean was during that time. So what did that do with the 2 intensity forecasts? On top, we show the SST from feature-based and RTOF's initialization. SST is slightly cooler in the feature-based, even though they relaxed SST. But maybe by a few tenths of a degree Celsius. But still, we see with the RTOF's initialization a substantial improvement in intensity, particularly for maximum wind speed. We see an issue of timing here in the second intensification, but the model storm moved too fast, so I think it compressed the time of the timing of the peaks there. But again, the improved initialization made a big difference in the projected intensity. And just to illustrate that the RTOS and feature-based initialization, it wasn't just SST, it's the thickness of the warm layer. The very thick warm layer really was extra layer of insulation that would tend to suppress the cooling beneath Blanca, and that contributed to the improved intensity forecast. Okay, so now third earlier study, the work done by Shiyama in the Bay of Bengal. In this work, we looked at the impact of initialization for a range of climatological ocean conditions that are present in the Bay of Bengal. Basically, we have this is an idealized study where we have the realistic Bay of Bengal, but the ocean is initialized horizontally homogeneous everywhere. So there are no eddies in this particular study. And then the different homogeneous initializations were representative of different subregions of the bay and two different seasons, the pre and post monsoon seasons. Again, the atmospheric model initialization was in this case, it was idealized vortex embedded in a large scale atmosphere at rest. And it's identical for all cases. We want to isolate the ocean contribution. And this shows how this was broken down. The Bay of Bengal was broken down into north, central, and south subregions. And when you do the realistic, the idealized initializations for these three subregions for the pre-monsoon and post-monsoon seasons, that leads to 6 cases. She also ran 2 additional cases where it was the average over all 3 regions, pre and post monsoon, so a total of 8 cases. Now, one thing to notice is that in this climatological sense, there is not a large difference in the ocean upper ocean heat content. The differences in SST are less than a degree in all of these cases. So at most, we might expect a modest ocean impact, intensity forecast impact on these differences. And indeed, that's what we see, where we have the minimum sea level evolution for the 8 cases. And we see that there is a modest impact, maybe differences reaching up to 20 plus millibars. To take a closer look at this response, we looked at an average over 2 days, hours 36 to 84, shown by the vertical lines, to summarize the differences in intensity. On top, we have the average minimum pressure that's averaged over those two days, as I showed. And you can see the differences in pressure after the storm reached quasi-equilibrium intensity. Modest impact, and actually impact post-monsoon is relatively small in the 4 subcases, larger pre-monsoon. And on the bottom, we show the time average SST and enthalpy flux. And these fields were also averaged over within about 2 radii of maximum winds beneath the idealized storm in the model. So we have a temporally and area averaged SST and enthalpy flux beneath the model, which again shows the differences resulting from the different initialization. Now, carrying this, given this information, we did, I think, an interesting analysis. The sample size is very small, so this is only really suggestive of the relationships that we're looking for. But if you graph the minimum pressure during quasi-equilibrium pressure versus the enthalpy flux, and the enthalpy flux averaged over the inner core region, you can see a very tight relationship with that maximum intensity and enthalpy flux. So not no surprise, because this is the heat being provided to the storm, and the resulting intensity closely follows the heat being provided to the storm. With SST, and it didn't show up here, but R squared for this analysis was 0.96. So even with a very small sample size, that's quite a very good fit. Now, if you do the same for SST under the inner core, you do see a relationship. It's not quite as tight. That's no surprise because, well, SST is important under the storm is important. It's not only SST, it's the atmospheric temperature and humidity in response to the atmospheric boundary layer. There are a couple of feedbacks going on. So SST is related to intensity, not as tight as enthalpy flux itself. So an interesting result with a very small sample size. So take it with a grain of salt. In addition to these modest differences, Shyama also looked at more extreme initial conditions in the Bay of Bengal. So she initialized the bay, homogeneous bay, with conditions representative of a cold eddy and a warm eddy that are typically found within the Bay of Bengal. Of course, here we see very large sensitivity to these extreme initial conditions. The resulting, with the cold eddy profile, the idealized storm did not intensify very much at all, whereas a very strong storm formed under the warm eddy conditions. So again, the ocean initialization does matter. So clearly, intensity forecasts are sensitive to ocean model initialization. And we can, if we hold atmospheric conditions constant, we can detect the ocean contribution even when it's relatively small. And what this does, if you take the next step, this establishes the importance of ocean observing systems for improving hurricane intensity forecasts. Because if the ocean model is not correct, obviously you can have biased intensity, and the simulation of ocean observations is going to be is an important tool in the future for improving intensity forecasts. Subsurface ocean observations, i.e. profilers, are critically important. I mean, correcting SST is not enough. We must correctly represent the heat potential, the thickness of the 26-degree layer. And also, I didn't mention it, profilers are important for correcting stratification in the model, which will enable the model mixed layer model to hopefully work or be more accurate in terms of representing the forced cooling. And also, this work provides the motivation for quantitatively assessing the impact of individual ocean observing systems existing and planned on intensity forecasts. And that's where OSE and OSE work comes in. Ultimately, our goal will be to determine quasi-optimum ocean observing strategies. We have existing ocean observing systems. We have new observations in terms of, for example, PHOD gliders. How do we optimally deploy those to potentially improve hurricane forecasts? And then other observing systems like airborne expendable surveys. We need to look at all of these to determine how best to sample the ocean, correct the ocean for initializing the ocean model, and hopefully improving forecasts. Okay, part two. So I'll talk about first the OSEs we performed for the 2017 hurricanes. And there are several experiments that we have run, the unconstrained simulation and assimilate all observations. That is our control experiment. And we're looking at simulating, separately simulating 4 different observing systems here. Argo profilers, PHOD gliders, SST only, and altimetry only. And the first set of fields that I show to look at the impact will be averaged over the middle of the 2017 hurricane season for over 21 August to 7 October. And I'll show these, and also after doing that, I'll show pre-storm fields for Irma, Jose, and Maria to get an idea of which observing systems are providing reasonable corrections to the ocean model. In terms of the heat potential, the upper left panel shows the observational analysis of heat potential. And you can see the ocean is quite warm. The panel underneath, the middle left panel, shows the unconstrained model. And it's clear the unconstrained model is too cold. Now, the other 4 panels look at assimilating individual components of the observing system. So we have lower left, we have Argo, upper right, the PHOD gliders, middle right, SST only, and lower right, altimetry only. And some things jump out. First of all, although altimetry does correct the eddy field structure, it does not do well in correcting upper ocean heat potential. Altimetry assimilation tends to emphasize correcting the main thermocline or the full water column temperature salinity profiles. It doesn't optimally correct the upper 100 meters where the hurricane action is. And this is a ripe area for future research to try to get better information on the upper 100 meters from altimetry. I think that would be worthwhile future research. Now, Argo is too sparse in space and time to correct the eddy field at all. But in terms of very large scale biases, there are enough Argo floats in space and time to improve that situation. SST only, yes, we see on the middle right, again, general improvement in the upper ocean temperature. However, a closer look at the water column shows that you're only correcting the mixed layer temperature, not below. So there's there's a lot to be said there. On the upper right are the PHOD gliders, and you can see the region around the deployment of the glider. I'll show you some more detail later, but you can see the correction that they're causing on the model. Typically over maybe a 2-3 degree radius, you'll have some significant correction from an individual platform in the ocean. Depth of the 26 degree isotherm, generally you reach the same conclusions here. Again, the PHD gliders actually do quite a good job at over a fairly substantial region to correct the 26 degree isotherm depth, since it was too shallow in the unconstrained model. Again, altimetry, although it puts the eddies in the right place, you don't get an accurate correction of the isotherm depth. In terms of SST, again, similar, the unconstrained model is too cold compared to the observational analysis, and this is from remote sensing systems, SST. And again, you see the PHD gliders correcting regionally. Simulation of SST, of course, you get a very accurate, when you're looking at SST, simulating SST gives you an almost perfect model, but don't look under the surface. Let's take a closer look at the gliders and what they are doing. So I have 3 columns of figures here with TCHP on the left, 26 heights with therm depth in the middle, and SST on the right. The top row is from the unconstrained model. The middle row is assimilating the PHOD gliders only, and very quick. And on the bottom is the difference. And here you can see a lot more clearly the correction that the gliders are making regionally. What this says is that it's no surprise that 1 or 2 platforms are only going to correct a limited region of the ocean. But what I see here is a judicious deployment of several gliders over an area, maybe in synergy with the existing Argo floats, can really, I think, help us map a larger region. So I see a lot of potential there for having gliders out each year, and of course now we have to do the work to learn more about how to optimally deploy them in terms of separation, where they should go. But okay, I'll look at individual storms here. This is TCHP pre-Irma on 2 September. The upper left is unconstrained model. The truth is the TCHP analysis product, and the difference shows you how just pre-Irma how the fact that the unconstrained model was too cold. But we see some substantial, not perfect improvement, but substantial improvement especially as you approach the islands. The data assimilation is tending to warm the model, bringing it closer to reality. One caveat here is that both the model and the product are both analyses, and neither is perfect. So this is our closest representation of the truth that we have, and there's enough here to show that we're moving in the right direction by assimilating the different observing systems. Again, in the lower right, PhD gliders, you show the regional correction prior to IRMA. It's interesting that the IRMA's path kind of went between the two subregions where the gliders corrected the ocean, that made the ocean model warmer as it should be. For SST, again, this is fairly similar results with the assimilation generally improving. Again, altimetry doesn't really, you don't expect altimetry to assimilate, to correct SST, obviously. You're correcting subsurface profiles, but generally each observing system has a positive contribution to improving the initial model. Now, for Jose, again, we see second panel down from the left, the truth minus forecast model. Again, the ocean is too cold compared to the observational analysis. Control, assimilating all observations. You see a substantial correction towards getting rid of the cold bias. Profiles only do a good job generally. Profilers here, it's Argo, PhD gliders, and Alamo floats, and XVT if there are any available. So this is all profilers. All profilers alone can give you a substantial correction, but in general, the coverage is not good enough to correct the eddy field. So altimetry plus profilers and SST is where you have the optimum correction. And again, and what's interesting about Jose is Jose actually passed over the region that was substantially corrected by the northern PhD gliders. We might expect to see an impact on the intensity forecast. And pre-Maria, again, basically the same results. The model's too cold, but control and assimilating profilers and SST and gliders substantially corrects the ocean. So the summary of 2017 OSEs, unconstrained model, significant temperature bias, inaccurate representation of the eddy field. Altimetry corrects the eddy field, but really doesn't adequately correct the upper ocean temperature salinity, especially in the upper 100 meters. SST assimilation corrects mixed layer temperature, but insignificant correction below, so you don't get the full picture from SST. Ocean profilers, they're very important, but in general, we need more space-time coverage from profilers, which again, by deploying more gliders, we can begin to fill in gaps in what profilers provide. But ocean profilers and airborne surveys can contribute significantly also. So basically, any improvement in ocean collecting ocean profiles ahead of a hurricane is potentially has a significant impact on intensity forecast. PhD gliders, each glider corrects ocean fields within a limited radius, but an array of gliders, if we deploy it synergistically with existing data sets, including other profilers, we can maybe begin to look at more detail at the three-dimensional mesoscale structure beyond what the correction that altimetry alone can provide. Altimetry does correct the horizontal eddy structure, but profilers are needed to correct the vertical structure within these same features. We need them. These observing systems in the long run have to work together to make sure that an ocean anticyclones and anticyclones and boundary currents, that the profiles and all of these features are reasonably realistic. So that's sort of what we need to work towards to significantly improve the ocean model initialization. Now, I'm going to say a few words about Hurricane Michael in the Gulf of Mexico, and we ran some observing system experiments listed here. Again, the unconstrained simulation. We also ran a simulation initialized by ocean climatology, where I ran a HICON simulation with strong relaxation of the 3D model fields to Navy GM4 climatology. And there are experiments where all observations were assimilated. We actually have two of those, initialized by RTOS provided by EMC and initialized by our in-house data assimilation system. And then we look at individual components of the observing system as we did before. Now for Michael, this looks at the conditions present in terms of the dynamics, the ocean dynamics prior to Michael, and compared that to climatology. The climatology, sea surface height and depth of the 20-degree isotherm are shown on the left, where you have obviously a very averaged loop current structure as expected, whereas the actual initial field, and this is provided by the RTOS product from EMC, you see a retracted loop current, a detached eddy, and a band of colder than normal water separating them. Same for, of course, the 20-degree isotherm depth shows the basically the same structure. So in terms of dynamics, you have a strong cyclonic flow not too far north of the Yucatan Strait, the strong detached eddy, and you have a weaker anticyclone nestled up in the northeastern Gulf. The resulting heat potential difference, you can see the ocean is generally much warmer than climatology, but primarily north of about 24.5 degrees. And yeah, with the heat potential on top and the 26-degree isotherm depth on bottom. And you can see in the difference, you can see structures associated with the anticyclones, the strong detached ring and the weaker anticyclonic at a northeastern Gulf. These were reservoirs of heat that Michael was able to take advantage of. And in terms of SST, again, the SST itself, you don't see the underlying dynamical structure clearly with the SST as expected, but you can see that it was much warmer than normal. And I have salinity on the bottom, although we have not analyzed salinity that much yet. Generally, it's very similar over most of the Gulf, but as you approach the northern Gulf with the Mississippi River outflow and plumes present, there you see some significant difference in terms of with data assimilation. So especially just west of Michael's track, we see a large lens of fresh water, presumably from the Mississippi outflow that was present. So the impact of the anomalously warm, what is the impact of the anomalously warm Gulf on Michael? And this is the one forecast result that I'll show today and leave the rest for tomorrow. We have an idealized twin experiment. HICOM generated a balanced ocean climatological analysis for initialization. And we compared a couple of forecasts initialized by climatology to the same forecast produced by NOAA-EMC that were initialized by the RTOS ocean analysis. And as you can see, again, here's the heat potential difference is shown on the right. And again, north of about 24.5, where the ocean is much warmer than normal, that is where you see a major difference in the predicted intensity. Black curve is the observed best track. The red curve is the realistic initialization with the warmer than normal ocean. But here we have two others for comparison. We have in orange, we have the ocean climatology initialization, the ocean being too cold to storm. Basically reached Cat 1, maybe minimal Cat 2, and that was it. Minimal Cat 1, and that was it. The uncorrected model did not fully capture the warmer than normal conditions, so it too produced a storm that was substantially weaker than normal. So the summary of Michael results, okay, basically with realistic initial conditions, the model storm reached category 4, a little bit short of where it actually reached in nature, but it was much closer to reality. Climatological initial conditions and unconstrained model initial conditions, the model storm does not come close to that intensity. Basically, I'm going to end my talk here because Mathieu will then take these results from the 2017 and 18 OSEs and look at a series of coupled forecasts and begin to look at not only the sensitivity to initialization, but the sensitivity to assimilating individual ocean observing systems. So we're beginning that work, and I think this is research that hopefully in the long run will give us a better handle on initializing the ocean model and improving intensity forecast. So to be continued tomorrow. Thank you.